Swastiastu. Hello everyone, my name is Benaya Batubara, and in this video I will explain about mechanical behavior, testing and manufacturing process properties of materials. In manufacturing, parts are shaped by applying external forces such as forging, extruding, drawing or rolling. Mechanical properties such as strength, stiffness, ductility and toughness determine how materials can be processed and used. As you can see in table 2.1, which compares the relative properties of metals, ceramics, polymers, and fiber. The tension test is the most widely used method for determining mechanical properties. By pulling a standard specimen until it fractures, we can determine elastic modulus, yield stress, ultimate tensile strength, ductility, and toughness. The diagram in figure 2.1 shows a specimen before and after the testing. And figure 2.2 illustrates the stress-strain curve with the main stages of deformation. At first, the material behaves elastically, meaning it returns to its original length after unloading. Beyond the yield stress, permanent plastic deformation occurs. The curve reaches its maximum at the ultimate tensile strength, then decreases until fracture. Ductility is measured by elongation and reduction of area. As shown in figure 2.4, these values tell us how much a material can deform before breaking. In reality, the cross-sectional area of a specimen decreases as it elongates, so engineering stress is not completely accurate. True stress and true strain are used to describe the actual state of material deformation. The equation sigma equals k times epsilon to the power of n represent strain hardening, where materials become stronger as they are deformed. The area under the curve represents toughness, which is the total energy absorbed before fracture. Figure 2.5 and 2.6 show example of true stress-strain curve of various metal. This is figure 2.6, which shows more example of the stress-strain curve of metals. Several factors influence stress-strain behavior. First, the temperatures. The higher the temperatures increase ductility and toughness, but decrease yield strength and modulus, as shown in figure 2.7. And second, the strain rate. The faster deformation generally increase strength, as is illustrated in figure 2.8. Some materials also show superplasticity, where they can elongate thousands of percent before failure. Other effects include hydrostatic pressure, which delay fractures, and radiations, which usually make materials stronger but less ductile. Compression. Compression tests simulate many manufacturing process such as forging, rolling, and extrusion. Ductile metals show similar behavior in tension and compression, but brittle materials are usually stronger in compression. Friction between dies and the specimen causes barreling, another effect known as the Bauchinger effect. It occurs when prior tension lowers the yield stress in compression. For brittle materials like ceramic, this test is often used as shown in figure 2.9. Torsion test measure how a material responds to shear stress. A thin tubular specimen is twisted, and the shear strength and shear strain are calculated. From this, the shear modulus or modulus of rigidity can be determined. Forgeability of metal can also be evaluated by the angle of twist before fracture, as illustrated in figure 2.10. Bending or flexure tests are especially useful for brittle materials, such as ceramic and carbides. The test can be conducted in 3 points or 4-point bending. As seen in figure 2.11, the property obtained is called the modulus of rupture. These tests help evaluate how brittle materials behave under combined tension and compression. Hardness is the resistance of material to indentation, scratching, or wear. It is not a fundamental property but provides useful information about strength and performance. Several hardness tests exist: Grinnell, Rockwell, Vickers, Knoop, Mohs, and Shore. For steels, there is a strong correlation between hardness and tensile strength. Ultimate tensile strength is approximately 3.5 times the Grinnell hardness. This is the diagram that shows the different types of hardness tests. They have a different indenter and the shape of indentation, the load, and their dedicated formula to count the hardness number. Many engineers failures due to fatigue, which is failed under cyclic loading. Even when stresses are below the static strength, repeated cycles can initiate cracks that grow until fractures. As and curve shown in figure 2.16 plot stress amplitude against the number of cycles to failure. Steels have an endurance limit below which fatigue will not occur. However, aluminum alloys do not have an endurance limit, and their SN curve continues to decline. Creep is the gradual, time-dependent deformation of a material under constant stress at elevated temperatures. It is especially important in turbines, boilers, nuclear fuel elements, and other high-pressure temperature applications. The creep curve shown in figure 2.18 has 3 stages: primary, secondary, and tertiary. Design against creep often considers the secondary stage, where the rate is constant. Impact tests measure the resistance of materials to sudden load. 2 common tests are the Charpy test, where the specimen is supported at both ends, and the ISO test, where it is supported like a cantilever. The absorbed energy indicates the material's impact toughness. Impact tests are also useful to determine the ductile to brittle transition temperature. Failure is a critical consideration in both manufacturing and service. Fracture can be ductile, brittle, or due to buckling. Ductile fracture usually begins in microvoids that grow and coalesce, leading to a cup and cone fracture as shown in figure 2.23. The presence of inclusions or impurities can accelerate this process. Understanding failure modes helps engineers select materials and process more effectively. Residual stress remain in materials after manufacturing operations such as welding, machining, or forming. These stresses can cause distortion, cracking, or reduce fatigue life. Heat treatment is often used to relieve residual stresses. During deformation, mechanical work is partly converted into heat. This heat affects the properties of materials during hot working process. Understanding the balance of work and heat is important to control manufacturing outcomes. In summary, mechanical behavior and testing of materials provide essential information for design and manufacturing. Through tests such as tension, compression, torsion, bending, hardness, fatigue, grip, and impact, engineers can predict how materials will behave in surface. By analyzing failure and residual stresses, we can improve product safety, performance, and durability. And this is the reference that I use for this presentation. And that is all of my presentation video. Thank you for watching. Om Santi 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 Om.